Hey guys, so you want to know how to connect this controller to a PC? Well, just buy this. There you go, video's over. Actually, let me first say that do not buy this. Do not spend your money buying this. At least for me, this has been a horrible failure because I connected this to my computer and I tried to connect my PS2 controller to it, and it completely lagged the hell out of the controls. When I was trying to press buttons or shake the analog stick, nothing would really register at the proper times. And so if I pressed a button, it might register like 5 seconds later after that press. So I don't know what happened, but well, maybe it was because I took one of these ports out, but you know, I'm just gonna say it's the manufacturer's fault. You know what's funny? I thought this would work better than anything else I would ever try, but once I plugged this in, it was just so shit that I couldn't believe I spent my money on this. The only good thing that came out of this was the PS2 controller plug that I obviously took out because one of these controllers, I have two by the way, one of these controllers I didn't want to cut the cable on, and so that's why I took one of the ports off. Alright, enough about this. Now I want to clarify something because I'm connecting this PS2 controller over to my computer to play a game. Your application could be different. So this video is supposed to be kind of like an overall ultimate guide on how to connect any type of controller, whether it be a PS2 controller or not, whether it be a DIY controller or not. Now, whether or not you're dealing with a homemade controller or you're dealing with something like this, which would be a serial controller, you have to consider all the ways that you can connect the controller to the specific thing that you want to control. So as far as I know, there's 3 possible ways of doing this. But I'm only going over 2 ways that I hooked up this PS2 controller to my PC. And this would be obviously to play a game. So this is the first way to do it. Right off the bat, you see this rat nest over here that I have with all these wires. But it's really not that complicated. But it does require more hardware and more effort to get this started up. However, it has a big advantage. So if you can see the microcontroller behind all these wires, you will notice that this is an Arduino Nano. So this is not a microcontroller that can be natively recognized by the computer. And we actually get around this issue by using some specific pieces of software that help us to transfer the signal that the controller is putting out into the Arduino and then routing it over to wherever it needs to go. Now, if you're working with a homemade controller, all of this extra hardware you will not need. So this really depends on your application. The only reason that I needed this extra hardware in order to properly communicate with this controller is because this controller is a serial and it clocks out data. It uses a clock and it has a serial connection, you know, because wiring for all these buttons and all these analog controls is just a lot of wires. Generally speaking, for each potentiometer you have 3 wires, and each analog stick has 2 potentiometers, and each button usually has 2 wires connected to it. So, you know, with 16, 17 buttons and 4 potentiometers, that is a lot of wires. And so I don't blame Sony for manufacturing this controller with a serial output. However, this also complicates things because we have to reintroduce the signal back into the Arduino. And I'll explain that in a little bit, but basically what's happening is this serial connection is being transferred over to the Arduino. The Arduino has a special library. This library was written by a guy named Bill Porter, which is really cool, by the way. I suggest you check out his website. And because of that library, we can easily communicate with this controller. Now from there, we combine the library that connects to this controller to the library that connects over to the software I mentioned earlier. Those two libraries, in order for them to properly communicate, they need the signal to be set on a pin rather than be connected in the programming itself. I hope that makes sense, because I need to reintroduce the signal because the signal needs to be on a pin. And so what I'm doing is I'm setting an output. I am setting that output to be controlled by the controller, and then that output is going back into the Arduino to like an input, and that is being read by the second library that communicates with the software that eventually goes to the game that we want to play. Alright, if your brain hasn't exploded yet, well, let's go on to the second option, which is far more easier. And this is the second option. As you can see, it's very simple. So right away, you can notice that we're working with a Pro Micro microcontroller. This microcontroller specifically has built-in native USB support. So that's HID support, a human interface device. It can be plugged in and right away be recognized as a keyboard, as a mouse, as a game controller, as anything you want it to be, really. And it makes it so much easier to code everything because the hardware is already just supported. Unlike the previous option, if you're working with a serial connection, then it's super easy to connect all of these buttons to the microcontroller in the code, and we won't have to use any external hardware like we did with the first option. However, there's a catch here. You have to be able to find a library that communicates with your specific controller. See, I was lucky, and there are already libraries out there that communicate with this controller, making it super simple to code everything in this microcontroller. But if you pick up some kind of third-party controller that uses a serial connection but is not USB, then you might have to write your own library to communicate that controller with your microcontroller. If you're working with a homemade controller and you're working just purely with simple buttons and simple analog potentiometers, then you don't have to worry about this. You don't have to write any libraries and stuff. You can directly connect the buttons and the potentiometers to the microcontroller, and they will be able to control anything that you want on your PC. This option, while it's really simple and really great, also has kind of a disadvantage, because if you want to scale this up, say you want more pins, right? Well, I don't know if there's any other options for getting a bigger board with this microcontroller that natively supports HID. And if there are options out there, chances are that, you know, that bigger board that natively is supported is kind of more expensive than the same bigger board that would not be natively recognized. And so that's why the first option is still really great, because you can scale that up to however big you want it, and it's still fairly cheap. I also mentioned there was a third option for doing this, and while I'm not going into depth on this topic, it's great to know this exists. Basically, what virtual USB allows you to do is to flash your AVR chip that's on the Arduino and make it recognizable to the computer as an HID device. People have made USB keystroke injectors, programmers, virtual keyboards and mice, and much more with this method. So let's go over the first option. As I mentioned, most Arduinos you will come across will not be recognized as an HID device. Usually, you will just see it as a COM port in your device manager. Notice how it tells us the chip it's communicating with, CH340. This chip is just a signal converter and will not tell the computer that the Arduino is an HID device. So to get around that, let me introduce you to vJoy and vJoy serial feeder. vJoy is a program that bridges the gap between any device that is not a joystick and an application that requires a joystick. So it basically emulates a virtual joystick that can be detected by your operating system. And the vJoy serial feeder, as the name implies, is a program designed to feed vJoy data and bridges the gap between the Arduino and the virtual joystick. The feeder also supports a bunch of protocols that are commonly used for flight controllers and/or simulators. Alright, so in the description I'll have this folder available to download, and once you download it, you can open it up and you'll see that there's 3 folders here. Now, the folder that really concerns you right now is the serial feeder to PCWay. Everything in this folder has everything you need to get started with this option. So you have vJoy over here, and you need to install that first of all. And you have the serial feeder over here for the vJoy, and that's all ready to go. You don't need to install anything here. And here you have 2 folders, and basically these hold 2 different files. So the one I modified for my setup and the original file that came with the software. So you can go into here, and if you click on this Arduino sketch, so you'll be presented with this. And this is really self-explanatory, and the guy who designed this is an absolute legend because everything is here that you need to know. You put in your analog inputs, you put in your digital inputs, and here we have our digital bitmap inputs, and basically what that allows you to do is on a single pin control up to 16 switches. But I don't use this option. I just do simple analog and simple digital inputs. And that's really all you need for a controller. And the rest you can add or subtract to this coding as necessary and modify it to your application. Now, once you're done editing everything, you can upload this sketch to your Arduino, and just notice how at the very top, this sketch is using the iBus library protocol. So now if we go back over to this folder and go to the serial feeder and open it up, we can see that our protocol is iBus, and that's what we need to keep the protocol on so the Arduino can communicate with this program. And then, simply find the right COM port, make sure it's on vJoy, and you can also use other controller emulators if you would like, but I just prefer vJoy. So what I have also done is included the sketch that I used to connect the PS2 controller that I'm using to the Arduino. And just notice that we have the iBus protocol over here, like I mentioned earlier. And here we also have the PlayStation 2 controller library that defines the protocol for how the PlayStation 2 controller and the Arduino communicate. And in order to connect both of these libraries, we have to do this outside of the code. And this is primarily because the iBus protocol library expects a certain signal on a pin, and there's no way to really connect the controller directly to this iBus library without using a pin. Like, we can't do it in the programming, we can't do it in the code. So what I'm doing to bypass that and connect these 2 libraries together is to reintroduce the signal. So I'm setting up outputs and then sending those outputs back into inputs on the Arduino, so sending the signal back, basically. Now, it's easy enough to feed the Arduino its own digital signal, but what about analog signals? Well, that's where it gets tricky, because the Arduino can only operate fundamentally with on and off signals. The closest it can get to analog voltages is creating a PWM signal with an adjustable duty cycle. Thankfully, we can still use that to help us generate a true analog voltage. Here's what I did. I looked at some circuit boards from audio equipment, and I found this BU4066BC chip, which is basically an analog switch. It allows you to feed in a PWM signal and some analog voltage and control that voltage with your signal's duty cycle. I took some resistors and capacitors off too, and I built this circuit which allowed me to map an analog signal in the serial feeder program. Alright, so now that we have all the signals that we need, we just have to map them. And how you do that is you go into the vJoy serial feeder, you select the proper COM port that your Arduino is on, so my Arduino Nano is on COM 3, and then I hit connect. And at the very bottom, you should be able to see how many channels are available, and this is based on how you configured your sketch that you uploaded to your Arduino. To see the channels better, you can go to Channel Monitor, and you'll be able to see all the relevant channels that correspond to pins that are getting signals on them. As you can see, I'm moving the joystick, and that's our y-axis, and that is our x-axis on channel 1. Then channel 3, we have a button, and channel 4 and 5 is the same thing. We have buttons on there. And now we have to map them. So we have our signals on the channel, and obviously the program can detect that, but we still have to map them. And what that means is you have to add buttons. So we have 3 channels that correspond to buttons, so let's make 3 buttons, and select the appropriate channel for those buttons, so 3, 4, and 5. And then you can select which button you want to use. So I'll just do 1, 2, and 3. Really doesn't matter. And then we have to set them up. So this is the important part. So you have to know which button you are pressing. Okay, so right now I'm pressing the triangle button, and that triangle button on the PlayStation 2 controller corresponds to channel 3. So I'm just going to go into Setup. And as you can see, we are getting a value of 0 to 1023. I hit Calibrate, and it just tells you what to do. Set it to the off position, so I click Next, and then set it to the on position. I hit that button, and I hold it, and then click Done. And now, this button turns green when I press the button on my controller. So now we just set it up for every single button on the controller that we have, and we can see that it's responding to all the presses. So now we have to map the analog signals, and as you can tell on channel 1 and 2 where our analog signals are, they're kind of shaky. They're not stable, and they're definitely kind of off-center. Well, the great thing about this program is that it doesn't matter. So we add an axis, and then it's already channel 1, that can be our x-axis, and we hit setup. Now we want our joystick to be centered, so we make sure it's symmetric, right? And then we hit calibrate and center the input and press next. Okay, so right now our signal should be centered, like you see here. So click next, and now what you can do is when you move the controller, when you move the analog stick, it will go to the very minimum and very maximum values and automatically map those values for you. So it doesn't matter if like you have a logarithmic potentiometer or anything like that. It maps the signal how it detects it. So it's really a useful feature in this case. And now we can see our X joystick axis is properly mapped. There you go. So now you can see that our X and Y joystick axis are properly mapped, and we can actually use this in a game already. So the only disadvantage, I guess, to this would be that you have to make sure this is running in the background in order for the program to feed vJoy these signals. But you know, all the signals are recognized, and speaking of vJoy, if we bring out the vJoy monitor, you can see when I press the buttons, there are corresponding lights to those buttons on the vJoy monitor. So that means that the vJoy program is getting those signals, which is great. And then our X and Y axis obviously works as well. So everything looks happy. And yeah, once you verified that everything communicates with each other, then you can go ahead and map all these buttons and analog signals to any game you wish to control with your controller.
Something strange is going on here. There were loads of monolith fighters inside the building. They were all in a trance and talking to a pile of trash. I examined this pile, and if you cut through the crap, it resembles a primitive antenna. It seems that someone talks to them through this antenna, and they believe it to be divine intervention.
First of all, when you buy the Pro Micro, get this version. The TQFP package is a larger chip, and from what I've heard is the better option because you are less likely to get shorted pins. Also, up till now, I haven't talked about how to connect the PS2 controller to the Arduino. Well, just follow these diagrams and don't forget the resistor between data and power. If you power the controller via 5 volts, use 1 kilo ohms. If it's 3.3 volts, use 500 ohms. So just go to the Pro Micro to PCWay folder, and the first thing you'll have to do is add this library to your Arduino IDE, and after you did that, then you can begin programming. So here you see I modified the original sketch for my PlayStation 2 controller, but I also made this joystick sketch for beginners that just want to see the most simplistic settings. Now, it's worth mentioning if your PlayStation 2 controller feels a little bit laggy, then you might have to go into the library and go into the H file and change. And in this section of the file, you will have to change the clock and the delay. The setting that worked best for me with the Pro Micro is 2 and 10, respectively. So with the Pro Micro, we don't have to deal with any external hardware. Now we just have to program all the buttons and the analog sticks, and we're done. As always, thank you for watching, and I hope you learned something. Anyway, I'll see you in the next one.